Okay, it's now time to talk about multimedia files. What does it mean? Well, if we have our signals, for example, the VHS of the 1997 Meatball Festival in Brescia, we want to store it inside a computer. This is an analogic source. We have to convert it into digital with the digital analog converter, as we said. And so we need some devices to do it, which is an audio interface, a scanner for images, or a dedicated devices for videos. And then we have to encode or decode it, if we are going backward, encode it as an encoded signal. For example, a uncompressed PCM signal or an MPEG signal. And then we want to store it on the computer. But in this way, we have two different objects. And when we watch a video, we are usually handling one single file. This is because the encoded signals are contained into a container. A container is a file that may be of many different types. So what you have to understand on this picture is that inside the same container, you can have signals encoded in many different ways. Some containers are standardized to handle many different encodings, and other containers types are defined in a way that only admits one kind of encoding. If you're using devices, for example, as a digital camera, the digital camera will do all of this operation internally and just let you pick with your computer a single file. But also in this case, all these operations are carried out. Let's focus now on these containers. How the operating system of your computer distinguishes between file types, between containers? Well, there are three ways, basically. First, by their extension. That is the last three characters after the last dot in the file name. So for example, if you have a file called picture.jpg, that JPEG is something that tells your operating system that that file is a picture that is stored in a JPEG container, and so the operating system can pick the right application to open and interpret your file. The nice thing about extension is that it is really simple, effective, but the drawback is that the user can, by accident, modify the extension of a file, and this is the reason why in Windows extensions are hidden by default. But nevertheless, it is a good thing to go in the folder visualization option and check show extension for known file types. Another way to distinguish between file types is the one, for example, used by macOS, which has hidden files that tells the operating system some information about the file you're handling. So for example, if we have meatballs.mpeg and wedding.mpeg, this strategy of creating hidden files let the operating system know that, for example, meatballs.mpeg must be opened with some application, while wedding.mpeg must be ordered with some other application. This is the nice thing about this strategy, but the drawback is that when you copy files around, you have to copy also these hidden files, and these hidden files may build up and clutter the operating system. A third way to distinguish between file types is by magic numbers at the beginning of the file. So it is not at the beginning of the file name, is the inside the file, is at the beginning inside the file, some numbers that provide a standardized way to distinguish between files. This strategy is usually exploited by single application. For example, image processing software, when we try to open a file with that software, will ignore the extension or the hidden files binded to this file and just open it and look at the first symbols at the beginning on the file, and those symbols will tell the software which file type the file actually is. This is the most safe way, probably, to distinguish between file types, but it enforces the operating system or the software to access actually the file, which may be a slow operation. Now that we know what a file type is, let's see the many different file types or containers that are around for different media. Here we have a table with the media type, the file extension. We are sticking to the extension strategy because it's the one understood by all operating systems, basically. Here we see which codecs, which mean which encoding and decoding strategies are supported by this container. And here we will see the typical codec found inside that container. I put a yellow star near containers usually used for processing stuff and producing stuff, and a green star for those containers mainly used to distribute stuff. So for example, we have WAV or AIF files, usually containing pulse code modulated, so uncompressed audio signals for working with audio. But when we want to distribute audio, we can use one of these three codecs. Actually, the OGG also supports a FLAC codec, which is a lossless codec. For pictures, we usually work with TIFFs or native formats of graphic software, which can handle uncompressed or lossless compressed stuff. But we usually distribute JPEGs, which have a lossy compression, or PNGs, which have a lossless compression. I personally suggest the PNGs because they have a very efficient lossless compression. For video, there are many formats, but we usually don't work with video-only stuff. We work with audio and video containers. And the most famous is probably the MP4, but also the Matroska format is very famous. It's very useful. The difference between these two is that if your computer crashes while you're recording an MP4, the MP4 is gone. While if your computer crashes while you're recording an Matroska file, what has been recorded until that point is still a valid content. So you can recover from crashes and stuff like that. Both these formats contain basically anything encoded in any ways, but the two most used codecs are this one, the H.264 and H.265 formats. I would like to take some time to talk about the difference between raster and vector graphics. Digital representation of images can actually be done in two ways. Raster graphic, which is what we saw until now, which is signal values are sampled, quantized, and stored as a sequence of numbers, such as pixel of an image or frames of an animation. Typical containers are JPEG, MPEG, GIF, etc. But there is another way of storing information, which is by vectors. It means that once some primitive components are defined, such as lines, points, shapes, signals are described as a composition of those line, points, shapes, and stuff. This for images. When we talk about vector animation, we add the concept of object position and motion paths for describing animation in a vector way. Typical container for vector graphics are SVG, EPS, AI, FLV, and also PDF sometimes. So just to see the differences, a raster image, a raster representation of this image without the green stuff, is just the pixels, can be a matrix of point, which is oh well, here I used 1 for black and 0 for white, but it's arbitrary. You can understand the concept. It's basically a sequence of 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. These things will end up in producing this image, and its vector representation is something that sounds like a line command from the point 0, 0, which is this one, 0 on the x, 0 on the y, from this point to this point, 5, 5, with a width of 1 pixel. So it's basically telling the computer, draw a line between those 2 points with a certain thickness, with a certain color. What happens when we stretch the image from this to this, I mean a resize of 10 by 10 pixels? In the raster way, we just take the information in 1 pixel and spread it across the near pixels, and we end up with a very pixelated image. When we render vector graphics twice as big as the original, we just scale these values. And so we obtain something which is always 1 pixel thick, but we updated coordinate. So it means that in raster graphic, a resolution, the concept of resolution is predefined, while there is no concept of resolution in vector graphic, because it's not the sampling of a signal. Rather, it is an abstract or mathematical description of the signal itself. Curves are not stored as pixel, but as equation that can be used to generate the pixel at any desired resolution. In fact, vector images to be shown on screen must be rendered into a raster image, since modern screen only can handle pixels. And this operation is usually done automatically by the computer. For example, if the slide you are seeing would have been a JPEG or a bitmap, if I zoomed in, you could see the pixels. But the slide you are seeing is made by vector elements. And if I zoom in into the slide, you can see there are no pixels shown, because all the text is a vector, is represented as a vector graphics, and so you can see it without seeing the pixel. But the image I use for background or for the logo of my university is indeed a raster image, and so you can see the pixels when you zoom in. This is basically the difference between raster graphics and vector graphics. So what's better, raster or vector? Well, you would be tempted to say that raster is ugly and vector is good, but think of this image. This is a picture I took in the Philippines, and to reconstruct this image in a vector way would be really a pain, because there is no automatical tool that does this in a decent way. I have to use a lot of symbols, of lines and points to recreate all the features and the nuances of this picture. So probably a vector representation of this image would take up way more space than the raster version, because I need to go really in the detail to recreate this peculiar image. And what about this picture? This picture is really well represented by lines and points and shapes. So probably in this case, a vector graphic is more suited to represent this kind of information. And what about this? If I remember correctly, this is a Rothko painting. And yes, of course, I can do quite easily create a vector representation of this. It would be even more precise than what he did, but doing that would lose all the nuances of the painting, which is what I'm actually really interested in. So what is better, vector or graphics? It really depends on what you are representing. So if you are representing pictures of arts, you can use raster. But if you are representing something very flat, it's probably less space demanding using a vector representation. So in this last module, we saw what a file container is and what types there are. We saw common file types and encoders, and we saw the differences between raster and vector graphics. If you didn't grasp something of these three aspects, please watch the video again. And that's it. This is the end of the lesson for today. Just to have a recap, we saw what a signal is, so something that varies in space, like light varying in space for video or pictures, or pressure varying in time for sound. We saw how we can convert these signals into the digital domain, basically by sampling and quantization, which for sounds mean that when I sample something, I limit the maximum frequency I can hear on the sound, and I limit the dynamic range of the sound before encountering a quantization noise. And for the images, I limit the size of the details I can see of the image when I choose the pixel size of the image. And for the quantization of images, I limit the number of colors I can use. Then we saw how we can encode information. We can have lossless encodings and lossy encoding, or uncompressed encoding. Uncompressed encodings are usually useful when you work with data, while lossless encodings are useful when you are storing data, and lossy encodings are useful when you distribute contents. And then we saw multimedia files, multimedia containers, which may be of many types, and you can just pick the one that supports all the encoded information you want to put in. With this lesson, you should have learned how to handle multimedia files, which may be very useful when you prepare augmented reality content, or when you work with multimedia data on your computer. That's it. I hope that you found this lesson useful and clear enough. And see you the next time. Bye bye.